his final defense. The topic is cryptography in small characteristic finite fields. And the committee, the PhD committee, is going to be Professor Alfred Meneses from the University of Waterloo, Profesor Julio César López de la Universidad de Campinas, Dr. Luis Julián Domínguez de CIMAT Zacatecas, and also Dr. Guillermo Morales, and Dr. Oliver Schutze, and myself from Silvestre IBM. So Thomas, please give us a presentation of about 40 minutes, then the committee will ask you questions, and later we will decide about this exam. Please start.
Okay, good afternoon. My name is Thomas Oliveira. So I'm here to present the doctoral thesis, which is called Cryptography in Small Characteristic Finite Fields. So my advisor is Dr. Francisco Rodríguez. We are both on CIMBE, and my co-advisor is Dr. Julio López. He's from the University of Campinas, Brazil. So before starting this presentation, so I'll give you some glimpse about what our work is about. So here we have cryptology, which is the science of secret communication. So we took a small area of cryptology called public key cryptology, and inside this group we took a smaller area, which is the small characteristic fields. So we had two approaches here. So the first one, the cryptography. So here we are trying to write schemes for performing secret communications. And cryptanalysis. Here we are analyzing the hidden structure between these mathematical objects in order to practically break it. No? So throughout my presentation, we are going to pass through all these topics, and I will say to you where we are when I'm throughout this presentation. Right? Okay. So. Okay, so at first I will give an introduction about why we select these sub-areas, and then the first part, which is called high-speed elliptical cryptography. We are going to talk about the lambda coordinates, which is a new set of coordinates that we proposed, and with this coordinate as our foundation, we're going to implement the scalar multiplication over two different curves, Gabor-Klingskott curves and Koblitz curves. And after that, the second part of the work, which is the cryptanalysis part, which is called the discrete logarithm problem. So we're going to analyze the security, implement some attacks in finite fields, which are pairing friendly, and elliptic curve and hyperelliptic curves. And finally, some final discussions. Okay? So as an introduction, why small characteristic fields? So first, what's a characteristic, right? For a given finite field K, the least positive integer n such that n times r equals 0 for every r in the field is called the characteristic of a field. So extension fields of small characteristics are very interesting for implementation of cryptographic primitives because their elements can be directly represented in binary or trinary number systems, and this is made that the arithmetic over these fields are very efficient in the modern computers that we have today. So given that these fields are very, very elegant and interesting in the modern cryptography, why they are not prevalent in the current real-world problems, right? So that's what the reason is, because they have also some structure which allows attackers or cryptanalysts to propose a wider and more powerful range of attacks. So currently we have the following scenario. On one hand, we have elegant structures that make fast and very, very efficient implementations of cryptography in different platforms, hardware and software. And on the other hand, we have effective approach for solving the mathematical problems beneath those problems, and this brings some concern on the cryptographic community. So in this thesis, we want to analyze the practical implications of these attacks in some structures, and at the same time we want to implement safe structures which are based in small characteristic field, and say that, demonstrate that these structures could be used in real-world protocols, libraries, and standards. Okay, so let's go to the first part of, it's called high-speed elliptical cryptography. So we're going to start with the lambda coordinates, which are a new set of projective coordinates for binary ellipticals. Okay, so to implement the scalar multiplication over elliptic curves, scalar multiplication in terms of efficiency is one of the most important operations here to implement. So one way of accelerate this scalar multiplication is by improving the arithmetic of points. So we have points in the curve, so we want to improve the effectiveness of point doubling and point addition, for example. So one interesting way to do that is by proposing projective coordinates, because with projective coordinates, the point arithmetic does not require point inversions. So point inversion is a very expensive operation in finite fields. So until our work, we have these three major projective coordinates for binary curves: the homogeneous coordinates, the Jacobian coordinates, and the López coordinates. So given an affine point, P, defined by these two coordinates, these projective coordinates represent this point by different forms. So before introducing the lambda coordinates, I have to introduce the lambda representation. So this lambda representation was introduced by Knudsen and Schroeppel, and can accelerate point doubling, point halving, which are point arithmetic operations, and also can be used for point compression. So let's have a elliptic curve defined over a binary field, given by this equation, and we have a point in the group of points, with some point coordinates that satisfies the equation. So the lambda affine representation is given like this. So we have the x coordinate and the lambda coordinate, where lambda coordinates represent this expression, x plus y over x. Okay. So the equation with lambda point represented in the lambda coordinate is like that. So okay, now we have the lambda representation, ready to introduce the lambda projective coordinates. So given a point in a elliptic curve, in a binary elliptic curve, so the lambda projective coordinates is given by these three coordinates at capital X, L, and Z, where x from the affine is represented by capital X over capital Z, and the lambda is represented by capital L over capital E. The equation of the curve becomes like this, and we know that we have x here, y dividing x. So the condition that x equals 0, in practice there is no problem with that, because the only point that satisfies this condition x equals 0 is this one, 0 and square root of b. And this point belongs to a subgroup of non-cryptographic interest because it's too small. Okay? So what's the advantage of these coordinates? So our coordinates, called lambda coordinates, outperform every other coordinate, including affine and the projectives, in terms of point operations. You have multiplications here, squaring, and you see that affine needs one inversion, right? And if you compare with the López coordinates, which were previously the state-of-the-art coordinates for binary curves, you also surpass through all those four operations: full addition, mixed addition, the point doubling, and also introduced a new operation which is called doubling and mixed addition, which can be done atomically, and is very important for the pre-computation in our scalar multiplication. Okay, now that you have these coordinates, this is the foundation for our implementation in the GLS curves and Koblenz curves. Okay, so let's start with the GLS curves. First, let's introduce briefly the scalar multiplication. So we have a point here in an elliptic curve of order r, and the size of r is about n bits, and the operation q equals k times p, where q is a scalar, is called point or scalar multiplication. It defines like this: adding the point to itself k minus 1 times, like this. if you are computing this operation in the traditional double knot method, so we need about n, where n is the bits length of k, n doublings, point doublings, and n divided by 2 additions. So given that the scalar is chosen at random, so the average density is 1/2. Okay. So the GLB method in 2001, these 3 researchers, Gallant, Nemrod, and Vanston, presented a method to accelerate the computation of the scalar multiplication using efficiently computable endomorphism. So if you have a curve which is equipped with an efficiently computed endomorphism, let's say psi, so applying psi to p is the same of performing this scalar multiplication, delta times p. So for some delta in between 2 and r-1, so we can perform this Euclidean algorithm to divide the scalar into 2 subscalars and compute the scalar multiplication like this. You have delta and the scalar, and you can divide these 2 subscalars like this. But delta times p is the same as applying psi times p, applying psi over p. So we can divide the subscalars into 2, into approximately of size approximately n divided by 2. And we can apply this 2 GLB, which is this method called double knot multiplication, and recode the scalar into nav, window nav, which is we transform from bits to digits, and we have a smaller density of this scalar. So we divide the point doublings between 2, and we have n divided by double bit plus 1 additions. So to do that, we need a curve which has efficiently computable endomorphism. So that's the GLS curve. So in 2009, this Gower, Leans, and Scott constructed efficient endomorphism for a broader class of elliptic curves defined over a quadratic field. They proposed for prime fields, but then Henkerson, Carabin, and Menezes demonstrated that these curves can be implemented over binary fields, so quadratic extensions of binary fields. So let's have a quadratic field like this, and the GLS curve defined over f to the power, or f of 2 to the power of 2m with m prime, and a point represented in lambda affine coordinates like this. So we have the coordinate x and lambda. But as we are in the quadratic field, so we have this element have 2 parts: the constant part and the linear part. Okay? So the endomorphism of GLS is called psi, and we can be computed very efficiently with just 3 additions, and one of these addition is 1. So it's a very fast endomorphism, and you can use it to accelerate our scalar multiplication. So before introducing the scalar multiplication, we need to form a fast base arithmetic. So for that, we wanted to implement a 128-bit security scalar multiplication. So we chose this polynomial here with degree 127, and this allows to perform a modular reduction very efficiently. Modular reduction are operations that are very required in the main field arithmetic operations like multiplication and squaring. And as a result, we had these timings. So you note that we have here is the base field, and here is the arithmetic in the quadratic field. So we had 42 cycles for multiplication in a base field, and for instantiating multiplication in a quadratic field, we need 3 multiplications. But see that 94 is less than 3 times 42. That's because our machines can take profit of this if you have the same operation being processed in different operands. For that reason, we can take profit of the internal parallelism of our modern high-end desktops, and as a consequence, this quadratic field arithmetic becomes very fast. So we chose our GLS curve like that, and this parameter b, which is in the base field. And in that, when we published this work, we had this scenario. We got records on non-time resistant scalar multiplication. We got records on non-time resistant parallel scalar multiplication, and also we had records on timing resistant over binary curves. After that, we improved these timings for timing resistant scalar multiplication, and we got record also in all elliptic curves under 128 peak of security level. Okay. Okay, this is the GLV method. Okay. So we wanted to explore another method of doing scalar multiplication. It's called Montgomery ladder. Montgomery ladder was proposed by Peter Montgomery for factorizing numbers with an elliptic curve. A nice property of this method is the fact that we maintain a difference of numbers, and because of that we can compute all the formulas only in the x-coordinate of a point. So we can make the formulas more efficient, and also we can make it very efficient in terms of memory. And also the Montgomery ladder throughout the algorithm, regardless of the bit of the scalar, performs the same kind of operation. So it can implement timing resistant scalar multiplication. What we have until our work is the algorithm called Montgomery LD, Montgomery proposed by López and Dahal. This Montgomery is used for binary curves and use point doubling for processing the ladder. But we have in binary curves one operation which is called point halving. And we wanted to use this point halving in this ladder because it's a very efficient point arithmetic. So we propose this algorithm. We pre-compute all the point halvings, and here throughout this main loop of the Montgomery, we simulate that we are doubling the points. But instead of doubling, we just go to the memory and find the point that we want, and we go throughout this main loop. So we go through this loop, and after that we recover. We just using the x-coordinate, so the pre-computation is just store the x-coordinate, and after that we recover the lambda coordinate. So we chose another GLS curve. Now we chose a different B because for Montgomery LD point doublings, we need to multiply some fields by this element, square root of B, where B is the curve parameter here. And so to make it faster, we chose a B such that we have a square root of B of 64 bit, which is the word size of our machine. So we have very fast multiplications. So our half and odd could not surpass the traditional double and odd Montgomery LD because point doublings in Montgomery ladders are very efficient. However, our point halving, Montgomery LD with half and odd use pre-computations which can be used for fixed point scenarios because we already computed, so it's very efficient in this kind of pre-computations. But it allowed also to implement 2 and 4 cores timing protected multiplications, which were some speed records for us. Okay, so this was about the GLS curves. Now we are going to another curve which is called Koblitz curves. So the Koblitz curves, also called anomalous binary curves, are proposed by Neil Koblitz and is represented by this equation here. And the Frobenius map, defined like this, we raise the both coordinates by the power of 2, can be used on Koblitz curve. So we have another binary curve which has efficiently computable unknowns. But as these isomorphisms are very, very, very fast, we can convert the scalar k instead of a set of digits, a set of bits. We can represent it through digits and a summation of digits multiplied by powers of tau instead of binary, instead of powers of 2. So we can convert the scalar and we can perform the scalar multiplication instead of doing double and odd, we can do tau and odd, where tau is a very fast operation. This was proposed by Solinas in 2000. So here is the algorithm of tau and odd. So you represent the scalar k in his tau adic representation, and then in this case we are doing a special representation called tau now. So the digits are 1 and -1. So if 1, we add the point. If minus 1, the digit is minus 1, we subtract the point. If it's 0, we do nothing of no additions, just the tau. So the density of this special representation tau naught is 1/3. So for that reason, this length of the k increases a little bit, but not significantly. So we have L taus plus L divided by 3 additions. Okay. So to this curve, what we proposed is a new way of doing time-resistant scalar multiplication in Koblenz curve, based on the work of regular recoding from Joy and Tunstall. We implemented this version in a standardized curve called NIS K283. So this is the time for the main operations on the curve. We do the Frobenius endomorphism, which is very, very fast, just 70 cycles. And we do the recoding using the window nav equals 5. It's about 9,000 clock cycles, but we just need to do once. And the point addition, which is the only 3 operations that we need to perform the scalar multiplication. So our times, we got the speed record over time-protected scalar multiplication over Koblenz curve. Because before that, the only way to do time-protected scalar multiplication over Koblenz curve is to insert them into the Montgomery LD, where you cannot exploit the properties of the tau endomorphism. So this is what we have done for the Koblenz founded by the regular tau recoding over F2. And next, we propose another family of curve, which it was introduced by New Koblenz in 1991, which is Koblenz defined over the F4. However, these families the implementations over this elliptic curve were never proposed, never published before. And the problem is that this doing point arithmetic over quadratic fields, we have seen that it's very efficient because it takes profit of the internal parallelism of the machine. For example, if you want to add 2 elements of a quadratic field, so we have this element and this element. So if you want to add C equals A plus B, we do exactly like this. So we have 2 additions in the base field and with different elements. Well, we are repeating operations here. So if you take this data here, which is the latest input of this operation, it's called XOR, which is the addition in binary field, we see that the latency in all these machines is 1. So it takes 1 clock cycle to finish this operation. But if you perform consecutive one operation after another, so we can do it. Each operation is completed after 0.33 clock cycles. So it's very important to have many same kind of operations being performed one after another with different operands. Okay, so the Koblenz of F4 is defined like this, where gamma is in F4, which satisfies gamma squared equals gamma plus 1, and A belongs to n. And the Frobenius map on those curves, like that, we raised the 2 coordinates to the power of 4. And we wanted to implement a 128-bit secure scalar multiplication on those curves. So we selected m equals 149. So the group order of this curve is like that. So this value and this value are prime numbers. So we used our subgroup of interest, this one, which has size of 254 bits, which are required to perform a scalar multiplication of about 128 bits of but as in GLS, before implementing this scalar multiplication, we had to implement an efficient field multiplication, field arithmetic. So we need a trinomial here, as we had in the GLS curve, because trinomials are very fast for modular reduction. However, we do not have trinomials of degree 149, which are reducible over F2. So what can we do? Well, we consider another approach, which is called redundant trinomials. So with redundant trinomials, you have a trinomial, for example, g of degree n, which factorizes into this g is not irreducible. So it factorizes into an irreducible polynomial f of degree n less than n. In this case, n for us is 149. And we perform throughout the algorithm reduction modulo g, which is a trinomial, which is very fast throughout the algorithm. And at the end, we convert the point coordinates to we bring the point coordinates to the field f to the power of 149. You doing modulo fx. Okay. So this is our trinomial gx. It is this trinomial, which is very fast. It factorizes into this huge polynomial here. It's a 69-term reduced polynomial, but we do not have to reduce in this way. So this modular reduction becomes like this by doing this modular reduction of g, which takes about 10 additions and 7 shifts, which is very fast. So as a result, we had this timings here. So we got 2 speed records on Koblitz curves, and a protected multiplication of Koblitz curves, and we need now to implement the 4 tau nav, which will improve this timing. Okay. So this is the first part of our work, which is this part here, cryptography. Here we wanted to construct schemes for the Western application. Now we are going to move to cryptanalysis, where we are going to explore the written structure in our mathematical objects in order to break those structures. So we're going to start with finite fields. So we're going to start with this here, with parent-friendly finite fields. So a discrete logarithm problem in finite fields is defined like this. So let p be a prime and k a positive integer, so q equals p raised to the power of k. So fq is a multiplicative cyclic group of order q minus 1 and has a generator g, which generates all of their elements. So the discrete logarithm problem states as follows. So given f, the field, g, the generator, and a random element there, which is h, which is generated by g. So we want to find this I here, with raising g to the power of pi, and we have h. This value of I, it's called the discrete logarithm of h in the base g, in the note of López. This problem is a very hard problem it's a hard problem in computer science. We do not have a polynomial time algorithms to solve. However, in the late 3 years ago, we had very important advances in solving this problem in fields of small characteristics. And so we wanted to analyze how it's the impact of those new advances into fields of cryptographic importance, which is very friendly finite fields. So we chose this field here to analyze 3 to the power of 6 times 509, which is proposed by Ahmad et al. It had a security bit of 128 bit before those new advances, and it was used for pairing-based protocols. So this is the scenario that we had. So these algorithms for solving the DLP are have sub-exponential time complexity. So their complexities are defined by this expression here. This alpha is very important because when alpha goes from 1 to 0, when alpha is 1, we have a full exponential algorithm. But when this alpha goes to 0, we have a completely polynomial algorithm. So we had before, in 1982, a time complexity with alpha equals 1/2. So the security level of this field was more than 300 bits. And then we had this Coppersmith algorithm. It's 1984, and this algorithm was practically the state-of-the-art algorithm for solving DLP during more than about 30 years. So during all these years, all that we have is the alpha equals 1/3, and there was approach for reducing this constant C. This constant C is very important in practice. You see that it had 134, then it goes to 103. So when this field was considered, the Coppersmith was the state-of-the-art algorithm for solving this field. But then Ju in 2013 proposed a new algorithm with alpha equals 1 divided by 4, and this was one of the major advances for solving the DLP in small characteristic fields. So we analyzed this algorithm over this field, and we found that this has just 58 bits of security, almost 50. So in the next step, we want to see how this algorithm works in practice. So we selected another ternary field of 6 times 137, and okay, the last records for solving this kind of field were by Hayashi et al. In 2012. They broke this 923-bit field, this one, in almost 150 days in 252 CPU cores. With this new algorithm, this new field, we had 1,303-bit field, and we want to break it using the Ju algorithm. So this field had in Coppersmith about 76 bits of security left. And this is an index calculus algorithm, so we represent the field elements in polynomials. First, we had a factor base. We found the logarithm, the discrete logarithm of this factor base using linear algebra. And then we want to represent a random field element of this field represent in terms of polynomials of degree of linear degree. So we have a process which is called descent. So we are representing our big polynomial, big degree polynomial, into polynomials of degree 1, because here we have these logarithms. So we could do all this process in only 888 CPU hours in just 4 clock cycles. And at that time we had the record of cryptography, breaking the DLP over fields of cryptographic interest. And then we try another bigger field of 1,551 bit, and we succeed in finding a logarithm in just 1,201 CPU hours. This field was very important for cryptography because it was proposed by the literature, and our analysis added further weight to the claim that these fields are not suitable for cryptography. Okay, and the last part of our work is here. We analyze the security of binary elliptic curves and hyperelliptic curves. So the discrete logarithm and elliptic curves are different. So we have a curve E over a field F, a generator of this curve of order R, and a challenge point Q in this group generated by P. So the DLP on E consists in computing the integer delta such that Q equals delta times P. So we have different approaches, the baby step, giant step, and polar row algorithms. So there are classical algorithms, there are index calculus approach, and also isomorphism attacks. So there is the move attack, which reduces the DLP on the curve to a DLP on a field. So when this K here is small, this attack is very powerful because you have a sub-exponential and also a quasi-polynomial algorithm for solving DLP over fields of small particles. But here we analyze the biodescent-based algorithms. Specifically, the Gaudry has smart attacks, so we are reducing the DLP over elliptic curve to a DLP over the Jacobian of a hyperelliptic curve. There, we have sub-exponential algorithm for solving the DLP. So the most important algorithm is that. It's called Engel-Gaudry algorithm. It's also an index calculus algorithm. So we have a constructed factor base, you have to collect relations then, and after that, solve a linear algebra, and you get the logarithm. Okay, so we search to attack a GLS binary curve over this field here, which has parameters which are vulnerable against this attack. And the GHS attack produced a genus 32 hyperelliptic curve, like this one. And we select a factor base, by polynomial, so we select a factor base until degree 7, but we follow a different approach from the original algorithm, is to start the factor base as an empty set, and then throughout the relations we are adding polynomials there. Using this approach, we could finish the relation collection phase in just 44% of the factor base originally produced, which we would need to collect in the original algorithm, and we could solve this logarithm in about 284 seconds. Okay, so this was our work. So let's move to the conclusion and some final discussions. Okay, so our contributions in the field of cryptography was a new system of projective coordinates called lambda coordinates, which provide the state-of-the-art formulas. Now, this is the state-of-the-art formulas for binary curves. We designed a very efficient base and quadratic field. For this case, Q equal with the FQ of 2 to the power of 127. And we designed a novel right-to-left half-and-half Montgomery level algorithm, using for the first time efficiently this half-and-half algorithm. And we generate for the first time time-resist point implications for 4-core. Until that, we just had this for prime curves. So we have now for binary curves. And we proposed a regular tau-adic, regular recoding of Koblitz curves based on the work of Joy Tunstall, which was the base for our implementations of Koblitz curves. We proposed a construction of a new family of Koblitz curves defined over F4. And we take profit of this quadratic arithmetic. And also design arithmetic for this field 149 based for which one of the first based practical implementations using redundant triangles. And for the discrete logarithm problem, we analyzed those pairing friendly fields here with the new advances of breaking DLP over small fields. We apply these algorithms over those two cases that we showed before. Also, we implement the GHS attack over a GLS binary curve using just the magma algebraic system. It's a mathematical library. And we analyze the cost of this Engelbert algorithm for solving DLP over hyperelliptic curves, for solving the discrete log, but now we use in practice these dynamic factors. So our publications, we published the GLS and the lambda coordinates into this conference, CHES, in 2013 in the United States, and we had the honor to receive the best paper award in this conference. This work was extended to a journal of cryptographic engineering, and the Montgomery letter work was published in the conference SAC in 2014 in Canada. And now we intend to publish this Koblitz curve or F4 to the CHES conference of this year. For the discrete logarithm problem, our analysis of the field 3 to the power of 6 times 509 was presented in 2013, the pairing conference in China. These practical breakings of those two cases was presented in Wi-Fi 2014. Then we analyzed those two groups, which was proposed as 192 bits of security level on the Coppersmith algorithm, and we analyzed these fields under this new approach, and we published in a journal called Tiny Fields and Their Applications. Finally, the GLS attack here, which was this part, we presented in Latin Crypt of 2015 here in Guadalajara. So as a future work, in this part here, cryptography, we want to implement the tau nav, which will be faster than those 2 and 3 tau nav that we implemented before. We want to explore the limits of parallelism by implementing a multi-core scalar multiplication with more than 16 cores. We want to adapt our previously speed record of GLS curve into new platforms, and we want to recover this speed record. And we want to explore higher extensions of binary curves in high-end desktops and resource-constrained platforms. And for this logarithm, we are now practically trying to solve this DLP over 3 to the power of 6 times 509. So as I said, this field was proposed by Ahmad et al. To achieve 120 degrees of security under Coppersmith algorithm. So we already done the relations collection here in single stuff. We done the linear algebra of the linear, quadratic, cubic, and quartic irreducible polynomials thanks to the supercomputer Abacus. And now we are in this phase, the distance. So we are representing the polynomials into polynomials of degree 4. We already done this continuous fraction, the classical distance. We are now in this phase of representing polynomials of degree 15 to degree 4 using these two methods, Grosvenor base and powers of 2. So we are currently in this phase. Okay, as a final remark, I will put this phrase by Marc de Leglis in his class, How the Arithmetic Becomes Applied Science. He said, the history of cryptography is the battle between cryptographers and cryptanalysts. They are often the same person. So this is exactly what our work was about, was this battle of cryptography and cryptanalysis in small characteristic fields. Okay. So thank you, gracias, López.
Thomas, so we will start now with the questions by your PhD committee. And as is the tradition in Simvestar, we will start with our guests. In this case, we start with Professor Alfred Meneses. Alfred, if you want.
Thank you very much. Can you hear me well?
Yes.
Oh, that's good. So I like the presentation, Thomas.
Oh, thank you.
So I should ask, how much time do I have for questions?
Unlimited.
Well, no, that's
plenty,
that's
plenty, let's say plenty.
Yeah, I'll ask a few, and then if this time at the end I may ask some more when other people have had a chance. So, just do you have any thesis with you?
Yes, I have.
Yeah. I'm looking at page 63.
63.
That's the version you sent me in December.
Yeah. $63?
Yes.
Okay.
So the first paragraph, so when you pick these scalars, you have this heuristic for picking a random scalar. You represent it, you pick it over Z10.
Yes.
Yeah. Yeah. So, and the heuristic is that it's uniformly distributed. How do you verify that heuristic?
No, this is still a heuristic of this work. We still have to analyze more concretely this distribution.
Okay, because this can be very important, right? Because there are attacks on scalar multiplication if the scalar isn't uniform.
Yes,
For
that's
example, the first few bits of 0 that you can easily find, you can break things in signature schemes.
yes, that's
Especially for signature schemes, it's important for the scalar to be. So how would you verify this heuristic if you wanted to? Some experiments or?
well, we have to think about how to do it, but well, we have not thought about how to do it yet. What we're doing now is to doing the recoding instead of proposing it, because we do not have an answer for that yet. So we are not considering our timings, not doing this recoding.
Oh, I see.
So,
Okay.
but we need to think about this yet. We have to see how can we do that.
It might be interesting theoretically to study the distribution of the integers when you pick them from Z10 directly.
Yes.
Anyways, so my next question, just on page 80. your table 4.12.
Table 4?
412
Oh,
on page 8.
okay.
So one first question is, so for your implementation of arithmetic in F2 to the 149,
Okay.
you went to a bigger field, 2 to the 192, to get the irreducible trinomial.
It was not a field, it was a ring of polynomials because they're not reducible.
Oh, that's right. Yeah, yes, that's right. But you went to, yeah, that's right, degree 192
Yes.
to get the trinomial.
Yes.
But why couldn't you use a pentanomial over 149?
Yes, there is pentanomials, but experimentally we had very expensive. The cost of the reduction was not very fast. It was expensive, and this polynomial here, it's 192, and until 192 we have the same cost for multiplication because we have three 64-bit words there. So multiplication is the same, but after that using the shift and add multiplication, we have to do more additions and more shifts in a pentanomial, right? However, if we had in the next platforms like Skylake and Brodo, we haven't checked our implementation there, but there we have faster scareless multiplication. If such is the case, we can do multiplication by doing mul and add instead of shift and add. In that case, it doesn't matter. We can use pentanomials, for example, and we can avoid redundant trinomials. It's just a matter of with shift and add, trinomials are much faster than pentanomials. And these trinomial here are very friendly for us because 192 is 0 mod 8. So we can do byte shifts.
Yeah, thanks. I missed the fact that you're using a 64-bit machine, so multiplication is the same
Yes.
in 149 or in 192. So that explains things for me. So also with that table, can you just, so in the end, your F4 to the 149 Koblitz curve is quite a bit faster than the F2 to the 283.
Yes.
Can you just summarize at a high level why it's faster?
Basically, it's because of our quadratic arithmetic, because as we can take profit of the internal parallelism, so a multiplication here is faster than doing this multiplication in this field 283, and because you have to do we cannot reproduce, you cannot implement the same operation doing with different operands, and we can do it here in the quadratic field. So we cannot take profit of the throughput, the machine throughput. This will be just for desktop platforms, because with platforms which does not have internal parallelism, this will be probably faster standardized curve K283. The other reason is that because our modular reduction, which are present in very different field arithmetic, are very fast here, and in this curve 2 to the power 283, if I remember well, we do not have a trinomial, we have a pentanomial. So their base arithmetic operations are more expensive.
Thanks. How many processors did you use for the multiplication?
No, we used just one process, one processor.
So how many?
But then we have in a processor different arithmetic units that perform the same operations. For example, for XOR, I think in the Haswell we have three arithmetic units that we can perform.
And can you make it faster if you have more arithmetic units? Or
yes,
do you have more?
yes. Because currently we use, for example, for doing multiplication, on this field, 4 to the power of 149, we have about 5 multiplications to be done one after another. So, but we do not have so much arithmetic units to perform those. So the throughput cannot be. If you have more arithmetic units, we have more throughput, and our multiplication will be faster.
That's interesting. So I guess as these processors change characteristics, the best curve to use can really change over time.
Yeah, it is.
Just really tailoring to the characteristics of the new platforms. Suppose you had a processor with unlimited number of arithmetic units. What would be the best field to use?
Well, if we could use if we had lots of arithmetic units, and also a bigger amount of registers, for example, the CPU memory, we could use higher extension fields, and we could process lots of operations at the same time, the same operations in different operands at the same time.
So by higher extension, you mean like F8 to the something?
Yes, exactly.
Oh, so
that's what I was thinking.
What about the F2 to the 5 times 50?
Yes, this would be great too. But, well, we proposed that because we saw that it has non-vulnerable parameters of elliptic curves against the GHS attack there. We have to analyze this F to the 8 to see if we can do it there. There are already in the literature, you have to and see if we can do it there. That will be a great, interesting field to implement.
And the base field arithmetic, would you do it by lookup tables or by exploiting this many arithmetic units?
Yes, the only operation that we do by lookup tables, the multi-squaring operation, it is done for inversion. We need multi-squaring for doing the Itotsuji inversion method. Well, this is because there is a lot of data we can store, and to do it by repeating operations will be very costly. So we done this by lookup tables. In the GLS, not in Koblitz curve, in the GLS we also perform the half trace operation in lookup tables for the same reason. However, for example, as we discussed it, we could process these multiplications. For example, if we could have a field, a binary field 2 to the power of 8 of times something, we could perform the multiplication there, which are very costly because you do not have a carryless instruction in very constrained platforms. We could do it by doing lookup tables very efficiently. So this field of higher extensions are very important in constrained platforms.
Good, it's an interesting field. I was going to ask some questions about discrete logarithms.
Okay.
So page 89 of the thesis.
89. Okay.
So the 2 to 1%, which I understand is sort of a very difficult stage of the descent.
Yeah.
We need a bit of some strategies. So why does the Zhu Grosvenor-Basis method fail for half the irreducible quadratics? Can you explain that 50%?
We have just 50% because for some fields that we have solutions, we have 2 solutions, and in a certain way, these elements like still the solutions of all the other elements. So for some elements we have 2 solutions, and some of them have they're not well distributed, each one with one solution.
So that can be justified. And similarly on page 90, the next page.
Okay.
So after your first strategy, the first strategy works for about 95%.
Let me see. I think we changed the... Ah, okay, we're two. Okay, second search, right.
So my version at the end of the first strategy, we just said about 95% all irreducible quadratics.
Yes, we have another strategy here. We state differently the relations in a way that we can get more solutions from the ones that we know.
So my question is just, can you explain the 95%? Is that just experimental, or is there a nice analytic way of explaining 95%?
Let me remember. Let me remember a little bit. Okay. So I remember. Okay, so we have, in this case, we have two options: to be irreducible or 2 degree 2 elements, right? So we need this 95% is the portion of polynomials that can be generated within this method that also descend using Grosvenor base, right? So if we descend 50% there, we have a chance here. I don't remember the chance of being. Okay, I don't remember how is the probability of being reducible or reducible in 2 polynomials. But let's say it's half. But I don't remember this proportion. That's the only problem. But if we have this proportion, so we have we need to have in this. We need to have a probability of having in those 2 polynomials, right? So we need. I don't know if you see this. Yes. Okay. You can see, right?
Yes, I can see.
So let's see. I think there's also 4. Alright, that's it. No, I don't have. Okay. So, for 1/2, here it's okay.
That's it. Yeah, that's it.
For 1/2, we have we can descend using 2 to 1, right? The other one to be in order to descend them, we need this probability to say alpha from having, instead of irreducible polynomial, 2 degree 2 polynomials, and within this we need to have half times half, which is to descend both polynomials. So we have this. So this alpha must be something that makes 95%, which I don't know this property, this probability. I don't remember.
But anyways, that's fine. But in any case, it's an analytic number, probably that you also confirmed experimentally. So it can be explained analytically. So sort of related to that, can you go to slide 31 on your presentation?
Yes.
Or actually, or even the last sort of better to go to this slide. Slide 46, actually. Which is the current work on 3 to the 6 times 509. So in the estimates for 6 times 509, you estimated 2 to the 58 point something steps.
Yeah.
I know now you're doing a lot of work to try to complete the calculation.
Yes.
The question is, how close were the estimates to the actual computations? Time and difficulty levels. So what did you overestimate or underestimate and so on?
Well, until now we have to. The problem here is to correlate the steps into real timings or CPU timing for now. Right? Okay, based that we had this correlation from the last examples that we had broken in 3 to the power of 167, for example. Well, one of these operations here, the continuous fraction, we estimated that it could be solved in 1 month using our more than 200 nodes that we have. However, well, it's a probability that it happens, right? So the problem that this doesn't happen in almost, it was solved in 2 months. So, but the classical descent works very well in our estimations, and this descent worked very well until we realized that our logarithms are too big to be stored in the RAM. So we need to store in the hard disk, and now we do not have CPU hours anymore. We have, I don't know, what can I say, real time, because the access to the hard disk takes much longer than doing the CPU. So we are now trying to make this estimate of doing classical this descent of probabilities in powers of 2 to be. Now our challenge is to make them use as much as CPU as possible in order to be consistent with our estimate. Because we can do it, our estimate seems that we can do it here in 1 month also. But we feel what we have right now, we need, I don't remember the last estimates, but it's more than 3 months in 84 cores.
So it's a related question. Suppose you had more memory for your CPU. How much memory would you need so that your estimates, first estimates, were actually completely accurate?
Well, if you can do everything in RAM,
yes.
And now we transform all our logarithm values into binary form instead of characters. So we have currently about 250 gigabytes of logarithms, and we need to at least 250 more than that, because there are other processes that use this memory. So we need about that 256 about that gigabytes of RAM. But this RAM must be fast. The access to this RAM must be special, like the ones that we have in 5 of our machines here, because we have more machines, but the access is not fast, and that reason this is the bottleneck. It's because
it's still doable today. It's just that you don't happen to have the machines that's invested in, but
yes, it's very doable to break this deal today.
In theory, you could go buy some machines somewhere else and
sure. And like 2 times more machines than we had it, and it's
so in other words, your estimates were actually quite good. It's just the practical matter of not having enough RAM or machines currently in your institution. But that's it.
Yeah.
So it's a practical math.
Yes.
Okay. Maybe one more question on slide 42.
Sorry. Okay.
So this is, you implemented the GLS, the GHS attack on a special GLS binary curve.
Yes.
Defined over F to the 31. So it wasn't clear to me what the conclusions of that chapter was.
Well, we concluded that that the main conclusion here is it's very useful in practice to use dynamic factor base in the Engelberg algorithm. So it accelerates this algorithm very much using this kind of relation collection. And
but that's still a small field, right? So
yeah.
Extending that.
Yes, well, this is a small field, but the only other field in the range of 256 feet of security in the GLS curves that has of curves that have parameters that are vulnerable against the GHS attack are the 2 to the power of 127, exactly this one that we implemented in the GLS work. So our next step, one of our next steps, as described in the thesis, is to estimate concretely this, how to break this by doing real implementations of the base operations in the divisors that are needed in the Engelberg algorithm in order to have this time for doing that.
I see. So that's your next step, is try to implement the GHS attack for weak curves over F2 to the 127.
Yes, this is what we wanted the next step in this area.
Okay, so thanks. That's all my questions for now.
Thank you.
Thank you, Alfred. So we continue with Luis Julian, please.
Thanks. Thank you very much for your presentation, Thomas. I have some questions regarding the lambda coordinates and the final fields, because you focus on the binary curves.
Yes.
And we'll find it the fields of binary fields, isn't it? And do you try these lambda coordinates on ternary fields?
No, we haven't done it for trinary fields. In fact, we didn't implement anything in trinary fields in this part.
But this is worth, you know?
Do you think are you asking if we should do it? If we should?
Yeah.
Are you asking if you should do it? Well, yes, we could do it. It's an interesting way. I don't know how this lambda will work there, but we haven't analyzed that. But yes, it's an interesting approach. Sure.
Yeah, but things that I work with larger characteristic fields, so I was thinking on the curve for pairings, for example, and you have these protected multiplications, and I don't know if, what would be necessary to do to implement these lambda coordinates on that kind of curves.
You need to verify the group order, the arithmetic there of points, and check whether if these coordinates can improve the efficiency of this arithmetic. I don't know how is the arithmetic, point arithmetic of point tripling, maybe. I think this is the point tripling. I don't know how's the arithmetic there.
Yeah, well, the things there, the half trace, I think it doesn't work quite nicely.
Okay. Okay, but the lambda coordinates does not require half trace. We cannot do, if in ternary fields we cannot do half trace, we cannot do point halving if the point arithmetic there is similar as the binary fields, which I don't know. I don't know how is the point addition and point doubling in affine coordinates in ternary fields. I have to check that to see if we can do it.
Okay. fair.
Just
But yeah, about larger characteristics, like.
okay. Large characteristic has other arithmetic formulas for adding points. Yes, we have to analyze these formulas in order to introduce another point coordinates. Unfortunately, we haven't had the opportunity of working on big characteristic fields in this thesis. So I'm not very familiar with arithmetic there.
Yeah, no, that's fine. In the thesis on page 27, there's only to check. You find some endomorphism, man. Was it hard to find it? Because that's another requirement for other kind of fields.
27?
Yeah.
Okay. Well, this endomorphism was proposed by Galbraith and Scott for prime curves, and this endomorphism was already analyzed by Henderson, Carabino, and Menezes in their paper analyzing Galbraith and Scott point multiplication. So we took the endomorphism that was already analyzed and studied, and we just adapted to lambda coordinates.
Oh yeah, then how you did that adaptation? Was it hard to do it or?
No, it was
just straightforward.
Yes.
Oh, I.
If you want, I can show you.
No, that's fine. And what about the coordinates? I mean, this is an effort now about using different curves, and how does that fit? These lambda coordinates fits in that kind of standardization effort.
Well, lambda coordinates can be used in any binary curves, or we can do it using Kovacs curves. But well, the problem is that there are some concerns on the cryptographic community right now of using those curves. So what we are doing is proposing these lambda coordinates over different curves and see that they are very useful. But in standards, we do not have a serious proposition to them. But for example, Kovacs curves will be very interesting to propose as a standardized curve using lambda coordinates, because they are very rigid in the sense of that we cannot choose parameters that could possibly have a backdoor there. So, yeah, the range of parameters for Kovacs curves are very limited. So it would be nice here to use lambda coordinates in those curves and propose them as a new standard.
Well, using these lambda coordinates, you had a very nice speeds. It was very efficient. They're very efficient. But what about the variables usage inside?
Yeah. Okay. Just a second. So here is the memory resource for all of those coordinates. So the capital letters are auxiliary variables. The small letters like A, B are parameters, and R are outputs, P and Q are inputs. Right. So we are considering that we need all of those variables at the same time in the memory, which is not true. We can optimize it. So for example, we are using, for example, in the Jacobian we have the auxiliary variable A, and then we do not need to use it anymore. Then we can throw it out. So we can do optimizations there, but I haven't optimized every formula, so I don't know exactly how many variables can be used at the same time. But considering that we are using all of these variables, at least once they are needed, and we need to bring it to the RAM. So the lambda coordinates are the most efficient coordinate system among the projected coordinates. See that for point doubling we need just 8 variables, while the most efficient coordinate system in terms of memory usage are the homogeneous. And for point field addition we need just 11 where the homogeneous is also the most efficient in terms of memory. So the lambda coordinates are very efficient in terms of memory too. But of course, this can be optimized, and we may need less memories, less memory.
Yeah, well, the thing is that not many people try to optimize that when they publish their work. For example, in the elliptic curve database, they don't. They usually, well, so in some cases they are, but most of the cases they just take A, B, C, D, E, F, G until they finish. But well, you have counted your own, so that's fine.
Yes, but it's very important for using constrained platforms because the memory. But for high-end desktops, there is no problem. We can use as many as we.
Yeah, for high-end is usually not a big issue.
Yes.
Made for constrained devices.
Yes.
Anyway, my last question is, it's on the DLP ad that you're launching. How long do you think it will take to finish?
The last one, the 509, right?
It's actually in your future work slide.
It is. Yeah. Well, now we are trying to improve the speed for reading these logarithms. We have a bunch of logarithms of quartic polynomials. So this, as said, we have 250 gigabytes of information to be read every time, and this information are not. We can see this information readings as random, so we cannot have like a certain. We cannot read this part first and then the other, some family first and then the other family later. So we are trying to improve the speed for reading these logarithms in order to finish this work in at most 1 month. That's what, and we have 84 cores to do that. Given that we have 84 cores, which is we have.
Yeah. Thanks.
Okay, thank you very much, Lucien. Diego, would you like to continue, please?
Yeah, may we see the coverage curves in slide 20? Yeah. For some special fields, are there some criteria in order to choose the parameter A, either 1 or 0?
Yes, the parameter A1 is defines as the group order, and this fact we need a group order which has which is almost prime. So maybe you need like this group be like 2 times a big prime or 4 times a big prime. So this A and equals 0, 1 needs to be, for certain fields we need to choose them in order to generate these group orders.
Yeah.
For not all fields has, for some fields, for A0 and 1 we do not have small,
because
almost
later you mentioned a parameter of the form A gamma, with gamma as being a solution of a quadratic polynomial.
yes.
And also it is the same case. When do you have a criterion to choose A and gamma simultaneously?
Yeah, the gamma does not impose this gamma does not impose nothing here in choosing the group. We can choose gamma as if you have a certain parameter 0 or 1, you can choose this gamma as long as it satisfies this equation here. So here we need to take care about this parameter here, A 0. For our case, A equals 1.
I see. And now in slide 25, number 25. Yeah. No, it wasn't 25. Were you... Oh yes, here you don't have degree 149 trinomials that are reducible over F2. How is it that you don't have? There is no at all? Or you
yes.
couldn't find some trinomial?
Yes, we can search through all these trinomials until degree 149, and we do not have a. It was this sentence was produced after experimental result. We looked through all possible degree 149 trinomials. So because trinomial for be reduced to F2, we have to be at one in the. So we just need to move in one. We need to move through all degrees from 1 to 149. It's very fast operation.
Yeah, okay. And later you were considered an order of the group Q, which was 2 to the 127, right?
Yes.
I don't remember exactly what that is.
It was about GLS 127. We chose for the GLS field.
And yeah. And you were considering also a quadratic extension of this field?
Yes, yes. This. So we considered a curve over a quadratic extension.
127 is 2 to the 7 minus 1.
Yes.
Is it relevant, this form of the parameter 127 for this results for this behavior?
Well, for the GLS to be safe against the GHS attack, this M must be prime. So, in order to get, we need a 128-bit security level. So the next prime here, I think is 131, maybe. I think it's prime. So, but this 131 can also guarantee about 128-bit of security. However, our machine that we implemented here, which is a desktop, has 64-bit word. So this field needs 2 words of our architecture, which makes the multiplication fast for. But if you include another word, because 131, we have 3 64-bit words, so we need a 3-word multiplication. In that case, it will be much more expensive than doing over this field.
Okay, so that's...
Thank you very much, Guillermo. So, Oliver, please. No questions? Okay, Julio, do you want to?
Thank you, Francisco. I just would like to go back to the page. Let me see here. You have page 135, several open questions related to efficient implementation. The third ones, are there more efficient approaches to compute the inversion operation in binary fields? I noted there are possible ways to use the new instructions in the new processor, like a Scala-Echo or Broadwell. Probably you have tried several times to improve the inversion. But my question is related, how you thought about some special instruction that you would like to put in the machines to improve these operations?
Inversion. Well, currently we use Itosuji, and Itosuji mode squaring, which needs to be the most fast way to do that currently is by doing table lookups and multiplications and, well, to increase the velocity of Itosuji, we could have an instruction that makes squaring multiply by us, because we are squaring and then multiplying.
So this will be a good thing to have an instruction to do this the same time.
Yes, if you
Okay,
have that,
this is
it
good.
could be a 3 operand, which is squaring the first and multiplying by the second and return. This will be great for Itosuji.
Right.
But it still will be, I think, it will be inefficient compared with multiplication and squaring and other operations, because you have to do many times such operations and you have to do table lookups. So, well, the best operations to be done is to have a parameter m that you put there and raise to the power of m minus 1, so we are done. But this will be out of question for us. So yes, this operation for me will be great.
Right, good, good. You have another open question here that I didn't understand very well. It is possible to compute the point halving operation in projective coordinates.
Yes.
What do you think about the, I mean, what would be the strategy to try to find an algorithm in that direction?
Yeah, well, we tried lots of things here when we are doing the GLS in order to have a point halving. The problem there is because we will need inversions to do that. Well, we need the strategy is to state the doubling formula in a projective coordinate, and as was done with the affine coordinates, try to reverse this. But it already...
Yeah, but do you believe that it's possible to find it? Because, you know, I was looking at maybe 15 years ago, the same problem, and the only thing at that time was to use the left to right to avoid this computation.
Yeah. Well, maybe another strategy is to find projective coordinates, even using more parameters, in order to find a formula that are efficient in point halving. Maybe it's much more expensive by doing. Imagine that we have a projective coordinates that it's very expensive for doing point doubling, but we could do it in point halving. It will be an option. Maybe selecting a projective coordinates especially for this operation, independently of the cost of other operations.
Yeah.
I haven't searched for this approach yet, but this
could be possible.
So we start by point halving and then let's see what we can do by point doubling and addition. I don't know. Maybe it's inefficient there.
Yeah.
Some approach that you can do. I thought on that when I wrote this question.
Yeah. Okay. Okay, Francisco, thank you.
Okay, thanks.
Thank you very much, Julio. Yes, I just have one basic question. Is 131 a prime number? Yes or no? Can you prove it?
Yes, let's.
Just to tease you.
Okay. How can I start this? So 12 is 144, okay? And then so we need to go to here to see if it's divided by this one. So we have 2, 3, 5, 7, 11, these primes. So 2, you can see that it's not divisible, 3 is not divisible, 5 is not divisible, and it's 7. So 1 to 1, 7 is 1. So here, no, we do not have it. So for 7 it's not. and 11 is also so it's not, it's prime. It's a prime number.
Yes, okay, thank you very much. Some questions. So, anyone has another question, Alfred or anyone else?
Sure, just one more question.
Yeah.
So with your discrete log computational work, which is very nice, hopefully you'll finish 509 soon, and that's a very important field for pairing-based cryptography.
Okay.
So what would be the next interesting targets for attacking finite fields of interest in pairing-based cryptography?
Okay. I considered one of them. Just 1 second. So I consider this field 2 to the power of 12 times 439. Okay, the Granger et al. So this DLP on f of 2 to the power of 12 times 367. So they had the relation collection in linear algebra, which took 47 hours plus. They say just hours, so I suppose it's real hours, and 4,896 core hours, this relation. So this relation collection will be similar in this field. So let's imagine that we have just 24 plus the core cluster as they had for this example. So we could do the relation collection in linear algebra for 10 days. I'm supposing. And then we have the continued fractions in classical. They descended from 368 to degree 8. They do it in 67 days using 24 cores. Okay, so it's doable. Then for degree H1, they took about 14 days using that. So what I thought, I have done a very rough estimation, it's not very concrete, but the relation collection in algebra we do exactly as they do, and the degree H1 we can do exactly as they done. So the only different method for us will be this section here, continued fraction plus classical disk. So we need to descend in this case using continued fractions. We can degree 219 polynomial. Well, for continued fractions we need 2 of them, but here I bring a heuristic. It's a method from Rodríguez, and we can descend using this 2 to the power of 57 bound that we used in our computations, which I consider that's taking 1 month. So we can descend from 219 to 22, then to 11, and then to 8, having this amount of nodes, which is not it's not rigid. These are like upper bound in number of nodes. So we can do it in about like 3 months. So using just 24 cores, we can do it by 3 months plus like 2, and here it will be 4. So we can do it in 7 months using just 54 cores. But we have more than that. We have almost 4 times that. So we can solve it in 1 month.
Would Abacus be useful for this?
Yes, Abacus can do our linear algebra, and we could descend the rest of the algebra. Oh, and also we could do the continued fraction. Well, not using the. Well, it's a risk. We don't know if this method from Aurora works. We haven't implemented yet, but we could do it, or using Aurora's method or the Waterloo's tree. We could do it in Abacus too, and descend the classical here in single style. I think linear algebra continued fractions there.
Abacus has limited memory, right? Per core, is that correct?
Sorry, can you again?
Is the amount of memory, RAM available per core, is that the...
I really don't know if they had a centralized RAM or a distributed one, and I don't know how much RAM they have per node. But in this case, in these two phases that we do not need much memory. We just need CPU power. That's why I consider those two parts of the descent inadequate. And then here, where we have more memory available, and we are guaranteed that we have more memory fast, we can do the classical and the rest.
So you convinced me 439 is quite easy.
Yes.
So next, what's next?
Well, there is this the 128 bit, which is the 1, 2, 3. But I don't believe in our estimations yet, because the linear algebra is too costly. We need to find ways to reduce the cost of the linear algebra, because doing each